liquids and solids. We should be able to do this quicker than we do gases because liquids and solids don't change as much. The particles are already close together in both of those types of materials. So in liquids, we say they have an indefinite shape. That means they change their shape. They're going to take the shape of their container, but they have a definite volume, so their volume stays the same. It doesn't matter which container you move it to, it's going to be the same volume, same number of milliliters. Random arrangement and close together is how you have to draw the particles, and here's an example of drawing them random. It's easier to show the liquids random if it's a mixture where you have two different things, like this is blue and green, so it's easier to see that it's random. Just make sure the particles are close together, closer together than your gas. Make sure they're random, more random than your solid would be. All right, they're not as interesting as gases because being close together, changing the pressure, changing the temperature isn't going to move the particles as much. One of the things we do talk about with liquids, though, is this thing called vapor pressure. So in vapor pressure, the particles in your liquid are moving around. And they're different from a solid because in a solid they'll be in fixed positions, but in a liquid they're free to change their positions and slide past each other. So some of these particles are moving, and they're moving with different amounts of energy, and they're moving in random directions, and some of them are bumping up against the surface. So they're bumping against the surface tension at the top. Surface tension is created by how well the liquid particles are attracted to each other. And when they push against the surface, some of them randomly have more energy than others. If they have enough energy to hit the surface with more energy than the air pressure pushing down on them, then they can escape. When they escape like that, lower than their boiling point, and this is really important, when they escape and turn into a gas at a temperature lower than its boiling point, we call that evaporation. So evaporation and boiling are both going to be a change from a liquid to a gas, but in evaporation you have this little extra part that it's happening below its boiling point. Evaporation is not on the phase change diagram. Don't label that flat part on the phase change diagram evaporation. All right. If we put our liquid into a closed container, so if you've got a jar, that's supposed to be a sealed lid, isn't that nice? Yeah. And you have liquid in here, and you seal the jar off, and these little guys are bouncing around in here, and some of them are escaping, and so you get a few of them up here. Eventually, you're going to hit a point where this container is full. It has as many particles in there as it can before they start to clump up. And when they start to clump up, they start to turn back into a liquid. They start to condense. And then that liquid rains back down. So you have particles leaving, and you have it start to rain up here, and particles come down. And if you take an instrument and you measure how much pressure these little particles are hitting the lid and the sides of the container with, that's called its vapor pressure. Vapor pressure is going to have a direct relationship with temperature. Vapor pressure has a direct relationship with temperature. So what would a graph look like with a direct relationship? Well, it's going to have a positive slope. Okay? If we heat this container, if we put a flame under here and we heat it, we're going to increase the vapor pressure. These particles will move faster. More of them will have enough energy to leave the surface. There'll be more of them bouncing around in here. They'll be moving fast enough that fewer of them will clump up and rain back down, and the pressure will increase. That's the vapor pressure, and you have a reference table that's going to show us vapor pressure of 4 specific substances. It will be different for each specific type of liquid. Okay, so the table that we're going to talk about is reference table H. So grab your reference tables and open it up to table H. When you look at it, the title of it is Vapor Pressure of 4 Liquids. So generally, if a test question is asking something about vapor pressure, this is the vapor pressure graph that you want, and this is where you're going to get information. If we take a look at the 4 substances they have listed on here, propanone goes by the common name of acetone. So we've used that one in lab. It's the one that smells really bad, and it is used in nail polish remover. Evaporates quickly because we can smell it. Ethanol is sometimes called ethyl alcohol. This is the one that is made during fermentation. Also evaporates quickly. Water, you know. And then ethanoic acid, also sometimes called acetic acid, and also sometimes will be referred to by its common name of vinegar. So acetic acid, also kind of during fermentation, but this is when bacteria get into your alcohol and convert it into vinegar instead. So those are the 4 that are listed here. These are the only 4 that they're going to ask you questions about their boiling points and their vapor pressures unless they give you some other chart. So these are the ones they want you to see. I also want you to take a look at this. They put this weird dashed line across your graph. So that's not really a normal thing to do. And they label it specifically 101.3 kilopascals. When you look, this side of your graph, your vapor pressure in kilopascals goes up by tens. So 10, 20, 30, 40, 50. They're very, very specific here that this is at 101.3 kilopascals. That's because, it should sound familiar, 101.3 kilopascals is the standard pressure in kilopascals. So on this graph, this 101.3 kilopascals is showing you where standard pressure is, and that's because this will be our normal boiling point. So we defined boiling as when the vapor pressure of a liquid equals the atmospheric pressure. The normal boiling point is standard pressure. So when you tell me that the boiling point of water is 100 degrees Celsius, that is water's normal boiling point. So here at the 101.3 kilopascals, water right there, when you drop down, it's 100. But if we were to change the vapor pressure, if we were to go to 50 kilopascals pressure, water's boiling point would no longer be 100. You would drop down here, and being careful that these now go up in 5s instead of 10s. This side are 10s, this side are 5s. There would be 80, and so this would probably be somewhere around 82. The boiling point of liquids is not always the same unless you're talking about being at the same pressure. So you kind of have to dissociate the idea of boiling being hot. They're not exactly the same thing. All right, there's another concept that we can see on this graph, intermolecular forces. The prefix inter here means between. So when we talk about intermolecular forces, we're talking about the forces between 2 molecules. If I have one water molecule and I have a second water molecule, the oxygens are attracted to the hydrogens. This force here that's holding the oxygen to the hydrogen between 2 molecules, not this guy, not this line that's holding the hydrogens on, but this kind of static cling force of attraction, is called intermolecular forces. The higher the boiling point, the higher the normal boiling point, the stronger the intermolecular forces are in that substance. So if we just look at our graph with our only 4 substances, acetone would have the weakest intermolecular forces, and the acetic acid over here would have the strongest intermolecular forces. Things with weak intermolecular forces tend to evaporate easily. It's very, very simple to turn them from a liquid into a gas because they're not holding on to each other as strongly. Things with strong intermolecular forces are holding on very tight to the other particles, so it takes more energy to get them to fly off and be a gas. For its size, water has very high intermolecular forces. The vapor pressure increases with increased temperature, so vapor pressure and temperature have a direct relationship. Normal boiling point is the boiling point at standard temperature and pressure. The two we're going to have to worry about are 1 atmosphere and 101.3 kilopascals. Torr and millimeters of mercury are just other measurements of pressure that you might also run into. And 760 torr or 760 millimeters of mercury are standard pressure for those units. You will sometimes see test questions that are going to ask you about the boiling points of water, and your first reaction is going to be 100, but if they're changing the pressure, so this question is talking about dropping the pressure to 68 kPa, you need table H. Anytime they're talking about vapor pressure, anytime they're talking about changing the pressure in the boiling point, you have to use this reference table. So if these are going up by tens, that's 50, 60, 70, that's the line for 70. We come across, making sure we're staying on the right line, and we hit water. Am I on the right line? Across, there's water, we're dropping down. Yep, 80, 85, 90. So we're just a little to the left of 90, so maybe 88 degrees. They're going to give you a plus or minus range for your graphs, but my suggestion is to use that technique where you use the corner of a piece of paper. Make sure you're staying on the right lines as you go across. You don't want to lose points because you slid off a line a little bit and are reading your graph wrong. Intermolecular forces, the forces between molecules. Strong intermolecular forces gives you high boiling points. Low intermolecular forces gives you weak intermolecular forces gives you lower boiling points. And out of the four on table H, acetone or propanone has the weakest, and the acetic acid has, or the ethanoic acid has the strongest. Solids are going to be even shorter than the information that we had on liquids because, again, the particles are even closer together. So solids are very tightly packed particles. There's very little space in between them, and this regular geometric pattern becomes really important. Make sure they're in a pattern. Notice this one's blue, green, blue, green. Make it very obvious that they're in a pattern and that they're close together. They have a definite shape and a definite volume, which means they keep their size and shape. Some things like water, when they make their geometric patterns, water is odd in that when it makes its pattern, it actually makes little hexagon patterns, so that they actually end up with these little air spaces in the middle, and this is where our little snowflakes come from, and why ice is less dense than liquid water. So that's very strange and unusual. Most substances, when they're a solid, will be more dense than their liquid forms. Water is an exception. Make sure you know that. And that's what lets water flow. Sometimes we have these things called supercooled liquids. They look like solids, they act like solids, but they don't have the crystalline pattern. So they don't have a crystal structure to them, but yet they're solids. So they call them supercooled liquids. Plastics would be your best example, and pure glass also. That's my dog Trip trying to say hello to you because he wants my attention. Glass and plastic are two supercooled liquids. So they act like a solid, but no crystals. When you heat a solid, the average kinetic energy lets the particles vibrate back and forth faster. Eventually, they vibrate fast enough that they can slide past each other. Once they start sliding past each other, they're liquid. That's called its melting point. When it happens at standard pressure, it's called the normal melting point. And that's it. Densities for solids, melting points, which are also the freezing points, boiling points, and condensation points you can find on reference table S. Most of the elements are going to be solids at standard temperature, so you can find those information about them on table S, what temperatures they'll melt at. It's going to be easy to find on which ones are liquids and gases because they will have melting points much lower than room temperature. And that's it for solids, liquids, and gases.